Hello students, welcome back to the chemistry class. In our today's session, we are going to discuss about electrolytic cell and the process of electrolysis. An electrolytic cell is an arrangement in which external source of voltage is used to bring about a chemical reaction. Since here external electrical energy is used, the reaction is non-spontaneous. And the process of decomposition of any electrolyte on passing current through its aqueous solution or molten state, that process is known as electrolysis. Here we see a simple example of electrolysis. During electrolysis, we dip two electrodes into an electrolytic solution. The electrode connected to negative terminal of external battery is known as cathode, and the one which is connected to positive terminal of the battery is known as anode. Here we have to remember, in case of galvanic cell, anode was having negative polarity and cathode was having positive polarity. But in case of electrolytic cell, cathode has negative polarity and anode has positive polarity. Now, when the current will be passed, then the ions present in the electrolyte will start moving towards opposite electrode. Positive ions will move towards cathode and negative ions will move towards anode. At their electrodes, they will get discharged and they will be released. The amount of substance deposited at an electrode, to calculate them, Faraday has given some law. So now we'll see Faraday's law of electrolysis. According to Faraday's first law of electrolysis, the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of charge passed through that electrolyte. Once again I am repeating, the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of charge passed through that electrolyte. Suppose if W gram of substance is released or deposited on passing Q charge, then we can say that mass deposited is directly proportional to charge. But we also know that charge can be calculated by taking product of current and time. So we can write here that amount of substance deposited is proportional to IT, means current into time. To remove this proportional sign, we can use a constant here, that is equal to ZIT. Here Z is electrochemical equivalent. Suppose current is equal to 1 ampere and time is equal to 1 second, or simply we can say that charge is equal to 1 coulomb. Then we can say that W is equal to Z. So from here we can define electrochemical equivalent, that electrochemical equivalent is equal to the amount of substance deposited at an electrode when 1 coulomb of charge is passed through that electrolyte. Or we can say that electrochemical equivalent is equal to the amount of substance deposited when 1 ampere of current is passed for 1 second through the electrolyte. So this was Faraday's first law. Now let us see the second law of electrolysis. According to Faraday's second law of electrolysis, if same amount of charge is passed through different electrolyte connected in series, then the masses of substance deposited at their respective electrode will be directly proportional to their equivalent masses. Here equivalent mass E is equal to the ratio of their atomic mass and valency. So we can write here that mass of the substance deposited according to second law, W, is proportional to E. Or we can write that ratio of mass of substance deposited to their equivalent mass will be constant. So we can use it in a way that suppose many cells are connected in series and same amount of charge is passed through them, then we can make a relation here that W1 upon E1 is equal to W2 upon E2 and so on for all the cells which are connected in series. So this is the second law of electrolysis. Now let us see a numerical based on Faraday's law of electrolysis. Now here is a simple example. Here we have to calculate charge required to obtain or convert 1 mole of aluminium ion to aluminium, or 1 mole of copper ion to copper, or to obtain 20 gram calcium from molten CaCl2. So we will see one by one. Suppose first one, we need to convert 1 mole of aluminium ion to aluminium. So we can just write the half reaction for that, Al3 plus. To reduce Al3 plus to Al, we need here 3 electrons. Now, if we consider as 1 mole of aluminium ion to give 1 mole of aluminium, then this will be 3 moles of electron. And we all know that charge present over 1 mole of electron is 1 Faraday. So here 3 moles of electrons are required. It means the charge required to convert 1 mole of aluminium to aluminium will be 3F. Direct answer we will get here. Same way, if we will try to convert 1 mole of copper ion to copper, we see here that to reduce copper ion to copper, we need 2 moles of electron. It means 2 Faraday of charge is required. If the charge is asked in coulomb, we can easily convert it into coulomb by just multiplying 96,500 or 96,487 coulomb. Then we will get the charge in coulomb, or we can write here in Faraday also. Suppose, see the third question. In this third question, we need to convert to obtain 20 gram of calcium from calcium chloride. So for that, we shall know here that when calcium chloride will be electrolyzed, it will give calcium ion and chloride ion. Now to convert calcium ion to calcium, we need 2 moles of electron. If we consider as 1 mole of calcium ion to give 1 mole of calcium, then here 2 moles of electrons are required. Now mass of 1 mole of calcium is 40 gram, and to obtain this 40 gram of calcium, how much charge is required? 2 moles of electron. So we can write it as 2 farad. So now it's very clear that to obtain 40 gram of calcium, we need 2 farad of charge. So to obtain 20 gram of calcium, suppose the charge required is Q. Now, since it is the case of direct variation, so we can easily calculate that 2 upon Q is equal to 40 by 20, that's equal to 2. So Q will be equal to 1 Faraday. It means to obtain 20 gram calcium from calcium chloride, we need 1 Faraday of charge. So these are simple examples for determining the charge required for a particular reduction or to obtain a fixed amount of substance. Now we shall see one other numerical. Now here is our second question. A solution of nickel nitrate is electrolyzed by using a current of 5 ampere for 20 minutes. What weight of nickel will be produced at cathode? Atomic mass of nickel is 58.7. So here we see that we are passing 5 ampere of current for 20 minutes. So first we shall calculate that what is the amount of charge passed here. So we shall start our solution in this way, that charge passed. First let us see how much charge is passed. We can calculate it by taking the product of current and time. Current it is given as 5 ampere and time it is given 20 minutes. So we can change it into seconds by multiplying 16. So we will get here 6000 coulomb. Now we see here in this compound nickel nitrate, the charge over nickel is +2. It means the half reaction for the reduction of nickel ion to nickel can be written as Ni2 plus gains 2 electrons to get reduced to nickel. Now we will consider as 1 mole of nickel ion is gaining 2 moles of electron to get reduced to 1 mole of nickel. Now since the molar mass of nickel is 58.7, so we can say here that 2 into 96,500 coulomb. That is 2 Faraday. That is 2 Faraday. This much charge is required to produce 58.7 gram of nickel at the electrode. Now, we have passed here 6,000 coulomb charge. So, let the weight of nickel deposited be W gram. Once again, I am telling you that when we pass 2 into 96,500 coulomb charge, that is 2 Faraday charge, 58.7 gram of nickel gets deposited. So, when 6,000 coulomb charge will be passed, W gram of nickel will be deposited. It is a case of direct variation, so we can calculate directly that 2 into 96,500 upon 6,000 will be equal to 58.7 upon W, or we can write that W is equal to 58.7 into 6,000 divided by 2 into 96,500. On solving, we will get it here about 1.825 gram. So, in this way we can determine the amount of substance deposited at an electrode. Question can also be asked to calculate the amount of charge required to deposit a fixed amount of substance. So, we can calculate in the same way for that also. So, you all shall practice some more numericals related to Faraday's law of electrolysis. Now, we shall discuss about the factors over which the product of electrolysis depends. Product of electrolysis depends upon the nature of electrolyte which is electrolyzed. Second, it depends upon the nature of electrode. Electrodes can be of two types, inert or active electrodes. Inert electrodes do not participate in the reaction. They just act as a source or sink for the electron. On the other hand, active electrodes participate in the reaction. For example, copper electrode is used during electrolytic refining of copper. It participates in the reaction. So these active electrodes are generally used in the refining process. So the product of electrolysis will be different when we use inert electrode or when we use the active electrode. Product of electrolysis also depends upon the oxidizing and reducing species present in the electrolyte. Generally, the reaction having higher value of reduction potential is favored at cathode. On the other hand, the reactions having the lower value of standard reduction potential, they will be favored at anode. But apart from that, there are few reactions which are kinetically very slow at the particular voltage, and to make it feasible we need over potential. So such reactions do not occur during the process of electrolysis. Now we shall see some examples of electrolysis. For example, we electrolyze molten NaCl. Electrolysis of molten NaCl. This is a simple one. When current will be passed through molten NaCl, it will dissociate into sodium ion and chloride ion. Now here there are one cation and one anion. Cations will move towards cathode and anions will move towards anode. So at cathode, sodium ion will get reduced to form sodium, and at anode, chloride ion will get oxidized to form chlorine gas. So this was the simple. But this is not the case when we electrolyze the aqueous solution of NaCl. So now let us see the electrolysis of aqueous NaCl. When aqueous solution of NaCl is electrolyzed, so sodium chloride here also it will dissociate into sodium ion and chloride ion, but together with that here water is also there. So water will give H plus and OH minus. Now at cathode there are two possibilities. Either sodium ion will get reduced to give sodium, or the hydrogen ion will get reduced to give hydrogen gas. The standard reduction potential for this first reaction is about minus 2.71 volt, and for hydrogen electrode we all know that it is equal to 0 volt. Now we all know that if two possibilities are there, then the reaction having higher reduction potential will be favored at cathode. So among these two, the hydrogen gas will be released in preference to the formation of sodium. So this reaction will occur and sodium ion will remain in the solution. So the final reaction will be the reduction of hydrogen ion to give hydrogen gas. But since hydrogen ions are obtained from water, so we will write a complete reaction here. Here water will give H plus and OH minus. So if we will combine these two reactions, we will get here H2O plus electron gives half H2 plus OH minus. So this reaction will occur at cathode. Is it clear? Now let us see for anode. For anode also there are two possibilities. Here chloride ions are also there, and here OH minus ion is there. So here also there are two possibilities to occur at anode. So now that we will see. At anode, either chloride ion, it will get oxidized to give chlorine gas. Here the electrode potential is 1.36 volt. On the other hand, the second option is there, that water molecule will get oxidized to give 4H plus O2 plus 4 electron. For this reaction, the value of electrode potential is 1.23 volt. Now we all know that the reaction having lower value of reduction potential is favored at anode. So here water shall get oxidized to give oxygen gas as it is having lower value. But this reaction doesn't occur. Actually, the over potential required for the oxidation of water to give oxygen gas is very high. That's why this reaction is kinetically very slow, and chlorine gas is released in preference of this oxygen gas. So we will see that when aqueous NaCl will be electrolyzed, at cathode hydrogen gas will be released, and at anode chlorine gas will be released. Oxygen is not released here due to over potential here. So sodium ion and OH ion will remain in the solution. Now let us see one more example. If we electrolyze the solution of sulfuric acid, then here also sulfuric acid will dissociate to give H plus and SO4 2 minus, and water will give H plus and OH minus here. So at cathode there is only one possibility, that hydrogen ions will move towards electrode and they will be released in the form of hydrogen gas, and this reaction will only occur. But at anode, again there are two possibilities, either sulfate ion will move or OH ion will move. So here two possibilities are there, either oxidation of water to give oxygen gas, for which the electrode potential is 1.23 volt, or the oxidation of sulfate ion to give peroxodisulfate ion, for which the electrode potential is 1.96 volt. Here the product of electrolysis will depend upon the concentration. If we have dilute solution where excess of water is present, then the first reaction will be favored, means water will get oxidized to give oxygen gas. But if we have concentrated solution, then the second reaction will be favored and peroxodisulfate will be formed. So in this way we have seen that what are the factors over which product of electrolysis depends, and few examples of products of electrolysis. After this, in your chapter you are having about cells, primary batteries, secondary batteries, and about corrosions. So that we will see in our next class. So practice some more numericals related to Faraday's law and practice this also. See you in next class. Thank you.